Hello, good afternoon. So I'm glad to be here. This is the second time I'm speaking at this festival. And today I want to talk about Elixir. And before I get started, just a quick show of hands. Who here have heard of Elixir? Oh wow. Is anyone using Elixir for something? All right, okay. Well, 2 years ago when I came at the event and I asked who heard about Elixir, we probably not even have like half of their hands up. So it's a great improvement. And who here has heard of Erlang and has done something with Erlang, programmed a little bit? All right, cool. So, so this talk today is not about how to use Elixir and to learn about Elixir syntax and so on. If you want to do that, you can go to the website, read the guides, read the documentation, books. There are a bunch of resources to do that. This talk is about how using Elixir is going to change the way you think about software. Okay, so Elixir is built on top of the Erlang Virtual Machine, and it leverages a lot of the properties of the Erlang Virtual Machine to affect how we write and how we think about software. And this talk is about that. Right? The talk is called Idioms for Building Fault-Tolerant and Distributed Applications. And what we're going to learn here today are exactly those idioms. Okay? But before we get to them, I want to have a quick introduction. Okay? So I am the creator of Elixir, and a lot of the questions I have is, why create a new programming language? Which problems are we trying to solve? And I want to talk about that first. Okay? So I've worked for a while on a web framework called Ruby on Rails, okay? And quite some time ago, at this point, almost 10 years ago, we had a version of this Ruby on Rails web framework. That was the version 2.2, okay? And one of the big features in this version is that we're saying Rails is finally thread safe. And what they meant by that is that, so why threads? So at the time, this was almost 10 years ago, we already had a pressure in the community for making Rails work on machines that had multiple cores, right? So we are at the time already starting to see machines with 2, 4, 8 cores, and people wanted to deploy their applications that were using Rails into production, and they wanted their application to use all those cores efficiently. Okay, that's what they wanted to do. The programming language there is Ruby, and in Ruby, the way you leverage concurrency, the way you can get your software and make it use all of the cores on that machine is by using threads. And so the idea of being thread safe is that you would get your application, you would use threads within your application, and your application would not blow up, right? And today I find it a very funny word, right? Because thread safe is about like the lowest guarantee you can give in software. It's like, it's not going to blow up. It's like saying, I want my software to be memory safe. Like, duh, yes, we want that, right? But that's the word we use to express thread safe. It doesn't talk about efficiency, okay? It doesn't talk about having good abstractions to work with concurrency. It just say, well, it's not going to blow up. And that's the guarantee that they can offer. So, I joined the Rails core team a little bit after this release was done, and it happened that Rails was, despite all this effort, it was not really thread safe, because that's something that is hard to guarantee in Ruby. So there were some people would come and report issues like, well, when I put a new server in production and there is a huge spike in load, I start to see those errors. And we would have a lot of reports with errors that are really hard to reproduce, which would make it really hard for us to solve them. So I was facing those problems, and then in my mind I was thinking, well, if concurrency is becoming more and more important, we are starting to see machines with more and more cores, I want to have better tools to solve those problems, okay? And especially today, this was 10 years ago, right? I like to say that today, 2017, everything we do with our computer should be using our cores. Right? I heard people complaining, my test suite takes too long. And then I'm asked, how many cores our machine has? 4. And how many cores are you using for your tests? 1. And they're like, we have the opportunity to make our test suite, in the ideal case, 4 times faster. Right? But they're not doing that. They're not using our machine resources. Oh, my server is not efficient. My application takes a long time to boot. And everything using only 1 core. It's not using the machine all the machine resources, okay? So I was on the journey. I need to find better tools, okay? And on the journey, I found about functional programming. And there's a lot we could talk about functional programming. Philip Waldner's here and is going to do a much better job than I could possibly ever do. But so I'm going to sum up in 2 bullets, okay? That to me, that's what mattered at the time, okay? So the first one was that the state became explicit. So we have objects, for example. One of the things you want to do with object is to encapsulate state, right? To put the state hidden inside the object and provide methods for manipulating that state. The problem is when you have a state that is hidden and hidden and hidden inside objects, it's really hard for you to understand how that state is changing through time. So we would have that there's some state somewhere where we have 2 cores trying to change that state at the same time, and then it would blow up. But it's very hard to find those cases. When I came to functional programming, then I said, look, state is explicit. We want to make it straightforward for you to reason about it. And a lot of those problems that were invisible to me previously, they became much more apparent. And not only that, even if we have a state, we are now thinking more about transforming. We're never mutating. In Elixir, if you have a list and you want to delete an element of the list, you don't take the element of you don't change anything in memory, right? You get a new list with that element removed. We are always transforming data. We are avoiding mutation as much as we can. So at this point, I was like, okay, like this, if I'm using those concepts in writing my software, it's going to be much more straightforward for me to write the code that I want to write and for me to reason about this code, okay? And then when I continued to study the different languages, different tools we have in the functional programming community, I really fell in love with Erlang, okay? So for those who are not fully familiar with Erlang, Erlang is a language and a runtime virtual machine that was created by Ericsson, which is a telecommunication company. And the nice thing about Erlang is that when they designed the virtual machine, the runtime, they had a very specific set of use cases in mind. So for example, one of the things that they wanted to build with Erlang was telephone switches. And what a telephone switch needs to do is that, for example, if person A wants to talk to person B, right, you're going to connect those 2 people that want to talk. They're going to be connected through a telephone switch, right? But you don't want the telephone switch to handle just one pair of people talking, right? You want to be able to handle many people talking to many other people at the same time. So you want to have many people talking concurrently and all being handled in a single switch. So, we start to see how, when they were designing this platform, how they had this idea of concurrency, how they had to solve the problem of concurrency. There are many people talking at the same time. Okay, that's interesting. But they also had to think about things like distribution, because sometimes you want to call someone, but that person is already talking to someone else through another switch, okay, far possibly. All right, so they need to have this mechanism for different switches, right, that are deployed, running live, to communicate between others. Say, hey, no, you cannot talk to that person because that person is busy right now, right? And there are a bunch of other interesting use cases. So, for example, in Erlang, we have something called hot code swapping, which is the ability of changing the code that is running in production without bringing the system down. Because it's extremely important for telecommunication, right? You always have someone on the phone. And you cannot afford to bring the machine down and disconnecting people who are on the phone right now just because you want to change the code. So you need to be able to change the code live in production without bringing that system down. And there are a bunch of other requirements. For example, they need to think about fault tolerance because sometimes they need to go places far away to deploy a switch and they don't want to go there every month to check something that is happening that is wrong, okay? And Erlang was used for telecommunication aspects, mostly for quite some time, until people realized that this use case that we have here, right, where we have a bunch of clients connect to a switch that needs to connect to other clients, this is very similar to the web, except that instead of having a telephone switch, you have a server, right? And that server needs to receive requests from a bunch of different clients. Sometimes it's a straightforward request from a browser, but sometimes you want to hold long connections when you're talking to a phone, and so on and so on. And then when people realize that those use cases, they are very similar, they started to use Erlang for the web too. And that's a lot of the use cases that we hear, like Amazon, Facebook, and we still have telecommunication companies like Ericsson and Motorola, startups like Heroku, and databases like Ryak. If you ever deploy an application to Heroku, every time you access your application deployed in Heroku, it's passing through a routing layer that is written in Erlang. Okay? And there's a case that got the most recent case of Erlang's success, which is WhatsApp. Right? They wrote some time ago this story about how they could have 2 million connections on a single machine. So WhatsApp is a messaging application, right? You install on your phone, you can exchange messages with your friends. In this case, they had 2 million devices, 2 million phones connected to a single node in production. Information was coming and going, right? And when you go to this, so the link for the blog post is here below. And when you go read information about that machine, right, you can see that's quite a powerful machine at the time. It was an Intel Xeon with 24 cores, 96 gigabytes of RAM, right? And that's exactly what we want, right? I want to write a software that is going to run as efficiently as it can on my machine that has 4 cores. But when I put that into production, it's a machine with 24 cores, it's going to use all those resources as efficiently as possible. Cool. So that's Erlang, and that's one of the many reasons why I really fell in love with the runtime in the ecosystem, okay? But this talk is about Elixir, right? So what is Elixir really? So we could say from what we talked about, what we saw, that Elixir is a functional language. But to me, it's much more than that. Elixir is a concurrent programming language. It's a programming language for concurrency. Or Elixir is a language for writing distributed software, okay? So that was the introduction. So now we're going to get to the really important part of the talk, which is when we talk about idioms, okay? So as I said, you saw this introduction saying, yes, I want to use Elixir, right? So how do I write software in this language? How do I need to approach? How do I need to think? What is going to be my mental model, okay? So let's get started. So here is the code that I was used to write in Ruby. That's likely the code that you write in Java, that in C, Python. It's a bunch of sequential code, right? And that's why using threads for concurrent programming is so hard, because you have the sequential code and you need to understand how the different threads of execution, they are going to interleave the sequential code. It's a complicated model when paired with the imperative programming, okay? So in Elixir, it's actually not much different, okay? We have sequential code. What we write is sequential code, except that we get the sequential code and put into something very tiny called a process. So from now on to the rest of the talk, every time I say process, I do not mean the operating system process. I mean a very lightweight, very cheap thread of execution that we have inside the Erlang Virtual Machine, okay? And we do not run only one process, we run multiple processes all at the same time, right? And that's how we get concurrency. We have all those processes that are independent from each other, all running at the same time, each doing whatever they're interested in doing, okay? And when they need to communicate, they do so by sending messages to each other, okay? So that's it. So if you're thinking about idioms, you already learned a couple of interesting words, right? We learned a new word, which is process, which is a very lightweight, very cheap thread of execution, right? And we learned about message passing, which is what those processes use to communicate. But there's more to learn here, okay? So let's go a little bit deeper. Let's get 4 processes here, okay? And let's zoom in. And let's imagine that all those processes in this case, they are part of a web application. Okay? So you can think that you have processes with different responsibilities. Some of those processes are responsible to talk to the database, so you're going to have a process with that responsibility. You can think that another process is going to be your TCP web acceptor that is waiting to receive connections every time a browser requests something, and it needs to handle that. You can think you're going to have processes to calculate the statistics about the users who are connected and what they are doing, and you are going to have processes that are responsible to talk to an external mailer server to send emails, right? And And this is common, right? If you write, if you wrote in any other programming language, you can write web applications with exactly all those components. The difference here, so for example, if you're using Ruby, if you're using Java, what's going to happen is that, what if something goes wrong with the mailer? What is going to happen with your code, right? There is a chance that if something goes wrong with the mailer, the thing that is responsible to send emails, it can bring everything else down. And when you think about it, it's really weird, right? Why an error in the thing that sends email can bring down the thing that is accepting web requests, right? That doesn't make sense. But you can say, well, that doesn't happen in practice, right? And the reason it doesn't happen in practice is because those libraries, those frameworks, they wrap your code. Every time they need to invoke a code that you, the user, write, they need to wrap it in things like try catch, begin rescue, to ensure that if something goes wrong, it doesn't blow up, right? But that's a very weird way of programming, right? Because we should reserve exceptions for exceptional cases, right? It's this practice of using try catch, begin rescue to ensure that your software is not going to blow up is, you know, it's like someone saying, you go into the doctor and say, hey, something is going wrong, something exceptional is happening, something is not normal, and then the doctor say, it's fine, continue doing whatever you're doing. I caught it for you, right? Begin rescue, try catch. So it's a very weird programming model and really adds a lot of bad habits to the programmer, okay? Here, however, in Elixir, we do things differently because we saw that each of those things, they are a separate process and they are independent. So what happens is that if there's something wrong with the mailer, we say it's okay for something wrong to happen in the mailer. Let it blow up, because if the mailer blows up, it's not going to affect the other processes. They are all independent. And what we do is that we create supervision trees, and each process is going to belong to a different supervision tree, and the supervisor is going to notice when something goes wrong, and is going to start a new one in its place. So if there is a problem sending an email, the supervisor, let that process blow up. The supervisor is going to look at it and say, hey, I can see that that process died. I'm going to start a new one so you can continue sending emails, right? And why does this strategy of starting fresh is so important, right? When your computer is not working, for some reason, like there is a weird flicker in the corner of your screen or something is not working as expected, what do? You restart the computer and then it works. Right? And maybe that problem never comes back again. You never see that problem again. Right? But restarting the computer fixes it. Because every time we restart, we go back to that initial step, right? That is well tested, that's guaranteed to work. And we are using the same strategy here. Right? We're not letting our software run when it's broken. We are restarting it. So, you know, we're talking about process, we're talking about supervisors, right? And then sometimes the supervisors themselves, they have more supervisors that have more supervisors. So at the end, we start to have those supervision trees that have our software structure. And then we package those things into applications, okay? So if we're talking about idioms, we've learned a bunch of interesting new words, right? That we already can see how they affect how we think about software. We are now talking about processes. We are talking about supervisors, applications, message passing. And we are gaining interesting properties. So we're now thinking about concurrency because those processes, they're all running at the same time, okay? We say now that we can fail fast. If something is wrong, we say, okay, it's okay for that mailer, it's okay for that process to stop working. We are going to start a new one in its place. And we start to see how we can write fault-tolerant systems. Because there are writing systems that can deal with failure. If something goes wrong, they are going to restart and go back to that working state. Because it doesn't matter what programming language you're going to use, especially when you're talking about building systems that needs to talk with the network, right? For writing a web application, you talk to the database. And sometimes the network makes the database disappear for 5 seconds, right? There is nothing you can do about it. It just happened. Network partition, right? So you need to be able to handle those failures elegantly. And restarting your service to ensure it goes back to that working state is a powerful strategy for doing that, right? So we gain all those properties. And there is one property that it's in the title of the talk, and I already mentioned, that we haven't explored yet, which is distribution. Okay, pause for a dramatic effect. So what about distribution, right? I said that we have all those processes that they are all running at the same time and exchanging messages between them. The way the runtime is designed is that when a process needs to send a message to another process, it doesn't really matter if they are on the same machine or if they are in different machines. The abstraction is going to be the same. And that's how we get distribution. And that's one of the main reasons that I got so fascinated with Erlang. Because we see a lot of new programming languages popping up that they are talking about concurrency, like, hey, we are here to provide better tools for concurrency. But Erlang is not worried about concurrency, right? They're not worried about the multi-core world. When Erlang was designed, you didn't have multi-cores, right? They're worried about distribution. Because when you write your software and then it's running on a machine, and then you buy the most powerful machine to run that software, and that machine is not enough, what do you need to do? You need to use more machines, right? So having this abstraction that allows you to handle concurrency and handle distribution, right, out of the box, can allow us to really be more productive when writing certain softwares. And I'm going to show some examples towards the end of the talk, okay? So cool, right? So those are the idioms that we need to learn, right? And now we are thinking about tolerance, we're thinking about distribution, we're thinking about concurrency. But the truth is, everything I said so far is true for any language that runs on the Erlang Virtual Machine. It's not something that is specific to Elixir. So for this last part of the talk, I want to talk more explicitly about why Elixir, okay? So in order to do that, I like to talk about the language goals, and we have 3 goals: compatibility, extensibility, and productivity. Compatibility, it's easy to talk about, right? So compatibility, it's everything I have said so far that comes natively from the Erlang Virtual Machine. It's going to just work in Elixir. We are compatible, right? You can call Erlang from Elixir and Elixir from Erlang and vice versa with no performance cost, okay? So that's compatibility. Extensibility, it's a bit more interesting to talk about, okay? And when I think about extensibility, there are many ways you can make languages extensible. And when we think about extensibility, I really like this quote from Guy Steele. It's one of my favorite talks called Growing a Language. I really recommend you to watch it. And at the end of the talk, he says, now we need to go meta. We should now think of a language design as being a pattern for language designs, a tool for making more tools of the same kind, right? Because computer science today, it's the things we can model with computer and what we can do. So my wife, she's a geologist, and she's using all kinds of software that are specific to geology, right? We have so many options, so many areas to explore that we cannot design a language that is going to go across all those domains, right? The point is that we need to have extensible languages that we can get and extend to the domains. The languages, they need to be extensible, right? It cannot be tied to something specific. So there are many ways to do that. One of the ways we do that with Elixir is by having macros. So here's the first Elixir code you're seeing on the presentation. And most of Elixir code follows this structure. First, you define a module. You say, well, this is a module called math-test. And you say, I want to bring the XUnit case features. And then you define the task that has a bunch of sequential instructions it has to execute. And depending on the programming language that you're using, you wrote unit tests very similar to this. But in many programming languages, you need to do things like, you can never do what we wrote here. You can never do assert 1 plus 1 is equal to. Because if you do that, you get a really horrible error report in case it goes wrong that says expected true but got false, right? So those languages, they have a bunch of assertions like assert equal, assert this, assert that, exactly they are requiring the programmer to give specific feedback so the tool knows how it works. But in Elixir, we don't care because assert is a macro, and as a macro, it can look at the code and say, hey, I can see exactly what this code is doing. It's trying to compare this thing with this other thing. And then if something goes wrong, you just use the same assert macro for everything. And when something goes wrong, we can provide a very detailed error report. Look, we're trying to compare this with this at this line, and this is exactly where they're different, and this is where we can find that place and more reference about the error. Okay? Other places are, for example, we have a tool in Elixir called Acto, which is about providing. So Acto is an abstraction for to talk to the database, especially SQL databases. And it's inspired a lot by LINQ. And LINQ is a language integrated query that exists in the .NET platform. Except that LINQ is a language integrated query. It's part of the language. But in Elixir, it's just a library. There's nothing in the Elixir language that knows about how to write queries in the database. So what we did is that we wrote this library completely separated from the language that can extend the language to write SQL queries. And that's how you write those queries in Elixir. Okay? And it's going to provide excellent performance guarantees. It's going to provide security guarantees because they're not going to allow you to pass, to do SQL injection to the database, and so on and so on. Okay? So we're getting the language and extend it to some particular domain. And we have a bunch of other tools beyond macros to talk about extensibility. And we can explore them if we have time later. But I would like to move to the third topic, which is productivity. Okay? And productivity, it's really hard to talk about, right? Because sometimes it's really hard for us. Sometimes there are good studies that show how some developers that have been much more productive using some particular languages, using functional languages, languages with types, right? But sometimes those comparisons, especially when you're talking about different teams with different knowledge, they're really hard to come to, right? So how can we say that a language is productive, or how can we say that I can be productive in a language, in a programming language? So in Elixir, we do that by providing a very good tooling. So one of the things that we do is that we say, for example, documentation needs to be first class. Documentation needs to be easy to write and easy to read. It needs to be accessible. I need to be able to access the documentation in different formats. You need to have very good tooling, right? Especially the tooling that is necessary for writing software, like, well, how I'm going to handle my dependencies, how I'm going to compile this project, how I'm going to do this. We need to have a good experience out of the box, okay? And we also need to, as the community grows, there is a chance that someone has solved the problem that you're working on right now, or someone has provided tools that's going to make your life much easier. So we need to be able to bring those tools into your application and allow you to leverage them when you're writing your software, which is what we do with Hex packages. Hex is the package manager for the Elixir community. So at this point, I have been talking for 30 minutes. So I want to have a pause and show a little bit of demo with all the things we have talked about so far. Okay, so all right. Da, 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 da. Yes. All right, beautiful. So for example, as soon as you install Elixir in your machine, you have the Elixir that allows you to run Elixir code, but you also have this tool called Mix that knows everything about building a new project and compiling that project, running the tests. So for example, you just start with Elixir and you say, people learn about all different kinds of ways, right? So I am the kind of learner that I like to go and mess with stuff and try to break stuff, right? And see what happens. That's how I learn. But there are a lot of people that they like more structured ways. They want to read the book and then they can better map the concept and move forward, right? If you like to learn by just go and playing with stuff and see how it breaks and how you can express yourself, so you can go to your terminal, you're going to say mix new, and you can start your project. And that's going to build a new project. You can go into the project directory and you can run mix test. And it's going to compile a project and run a test for you. So the default structure already tells you how you're going to organize different things. If I start a test editor in here, I don't think I can zoom in over the project structure. So let's do that from the terminal. All right. So for example, what you get here in this project, you get the README, you get a config directory, it's where you put your configuration files, lib is where you put your code, and test is where you're going to put your tests. And we have this file called mixexs that is your project configuration. Right? So here it says, well, here's the project, the version. If you have dependencies, you're going to just list your dependencies here. So, and here it's really straightforward. All this is about is you have a module with a bunch of different functions that return data about how your project works. So the tests, they are also straightforward. So here we can see a very similar case to the one we saw in the presentation. But I want to explore a couple different things. So one is, remember that we said that everything we do in our machines should be using all cores, right? So one of those things are tests. If I'm running my tests, I want them to use all cores if possible. And in Elixir, this is a matter of saying, well, I want this make this test async, and now all those tests are going to run concurrently. And that's something that we leverage a lot. So for example, when I'm working on Elixir, most of the Elixir, we cannot make everything run concurrently, but most of the Elixir test suite, it runs concurrently. And in my machine that has effectively 2 cores, it's really noticeable. If I run the test suite and disable the concurrency aspects, it takes 1 minute and 10 seconds. And when I run it with the concurrency using the 2 cores, it takes 40 seconds. And that's a noticeable improvement that I see every day. Every day that I'm using the software, every day I'm using the language, it's there. Something else that you can see here is this line called doc test. And doc test is really nice. So remember that I said that documentation needs to be first class, needs to be easy to write and easy to read. And here's how we have documentation in Elixir. We use those things called module attributes. So here I can say, here's the documentation for the module, and I can explain what this module is about. And then here's the documentation for this function. And I can provide examples. And those examples, they're actually tested. So what doctest does is that it goes for documentation, it finds examples, and tests them to guarantee that your examples are up to date. Okay? So for example, if I change this to bar, right? And now I run the test is going to fail because now the documentation and the implementation, they have diverged. So if you're talking about documentation being accessible, right? So one of the ways we can do it, so here we have this other tool called IX, and IX is the interactive Elixir. Here I can just write any Elixir code, okay? I can write and execute any Elixir code. So I said, well, documentation needs to be first class, needs to be accessible, and that's what we do. So here, if you type H my project, it's going to bring exactly the documentation that we have written there in our code. And you can use this to explore all libraries, from Elixir itself to any other library that you can bring in to your machine or to your project. So for example, imagine that you want to do some string manipulation, like instead of printing hello world, you want to print hello world in uppercase, and you want to have a function that does that. Well, how can I do that? So, I see there is a string module, and then from this string module, I can hit tab again and get the list of all the functions that string module. And then you look at the list and say, it's probably this uppercase function. Let me hit enter, and I can say, look, here's the documentation. Here are examples, and here's how I'm going to use this thing, right? So it needs to be really explorable and accessible, right? And that's going to really impact productivity. And here I'm showing the terminal, but that's not something specific to the terminal. We have editor tools that integrate with all this tooling to give you the experience in your editor. We have tools that take documentation and generate PDFs, generate HTML pages, so you can consume all these in different ways. All right, so that's one part of the demo. That's the part about productivity, have good tooling, and making the language easy to explore and get started, and so on. I have a bunch of other stuff to show, and I have time, so I'm going to explore about this other stuff. So what I'm going to do now, I'm going to come to this other project here and show a little bit more about the part about idioms. So we're saying, well, we have all those processes, and we organize them about supervision trees, we organize them in applications, right? And I said that changes the way we write software. So that part may have been too abstract. I'm going to show more concrete examples of how we write software this way and how we can actually use that for like debugging in production or understanding what our system does. So Elixir has a web framework called Phoenix, and I have a demo application written in Phoenix right here. So what I'm going to do is that I'm going to start my Phoenix application, okay? And I'm going to start an interactive shell inside this Phoenix application. And I'm going to start a tool called Observer. And one of the nice things about Erlang is that they are very good with naming. The names are very explicit, like the observer observes, the supervisor supervises. So, so what the observer tools does is that it provides you all different kinds of insights about your system, about the virtual machine, and about the software that it is running. So you can see here that we have many tabs at the top, and the first tab is giving general system information. What is the version of the runtime, how much memory it's using, how many processes are currently running right now. So remember that I said that we have a bunch of processes running at the same time. Here, just after starting, we're not even get any web requests, right? But just after starting, we already have 162 processes, okay? And we can see that the limit is about 250,000 processes that we can have at the same time, but you can increase this limit if you want, right? So here's general information. And we have a bunch of stuff like load charts. You can see there's nothing happening on this node right now because nobody's accessing it, but here is going to give you all kinds of information about about I/O, input, output, memory, CPU utilization, and so on. Okay, and then we can talk about memory allocators, the different places you're memory allocating, and so on and so on. I'm not going to go through all panes, okay? I'm going to show my two favorite ones. It's the process one and the applications one, and I want to show them to you. So the process one lists all processes that are running in your system, okay? And you can sort them and see, well, so imagine, for example, that the memory is growing. For some reason, memory keeps on growing. You are looking from the operating system, memory keeps growing and growing. And you say, well, where can this be? You can come to the process tab and say, I want to organize by memory. And then you have the process that is using the most memory first. Then you can double click it, and then you can navigate that process state and information and try to find why memory there is growing. And from there, you can go to the code and try to find the memory leak. Okay? Beautiful. So that's one way we can use the process tab. The other way you can use the process tab, and this is one of my favorite stories, is so Phoenix is a web framework, and it provides this feature where multiple people can exchange messages at the same time. And one of the benchmarks they had is exactly that benchmark that we saw from WhatsApp, where they got 2 million connections on a single node. And the Phoenix team said, hey, I want to reproduce this benchmark. I want to be able to get 2 million connections on a single machine. And they did that, and they wrote a blog post about that story. And what is interesting about that story is that when they started benchmarking their server to see if they could get to 2 million connections, the first time they did that, they could only get to 30,000 connections. Way below 2 million, way below. So what did they do? They started Observer in the remote node, and they came here to this process tab, and they said, I want to get the process that has the biggest message queue. Because when processes communicate by sending messages to each other, if one process is slow, if a lot of other processes are sending messages to it, its message queue starts to grow. So that's what the Phoenix team did. They clicked here, right? They started Observer, clicked on this tab, asked it to organize a message queue, and they could immediately see there was a bottleneck. We had one process that everyone was trying to talk to, and that's why they couldn't scale further. So they went, they removed the bottleneck, they did the same thing again, started testing again, came to Observer, found the next bottleneck, removed it, and they got to 2 million processes on a single machine, right? Exactly because all of our states, right, are in those processes, and we can explore those processes, right, visually here in the tool. So that's cool about process, but it's even more interesting is this view about applications, right? So remember I said we have processes, those processes, they have supervisors, and those supervisors, we build supervision trees that we package into applications, right? And here you can see, so in this demo Phoenix application, we have a bunch of in this Phoenix project, we have a bunch of applications running side by side, right? And one of those applications is the demo project itself, okay? And here we can see the supervision tree for our web application. Elixir itself is just one other application that has this very small supervision tree, okay? So what is interesting is that now I can come here and say, look, I can see how my application works, how it's structured. It has a supervisor, it has an endpoint, and the endpoint is the entity responsible for accepting app requests and so on. And it also has a repository, right? And the repository is the thing that we use to talk to the database. Because if you're building your application, it's very likely that you're going to talk to something like a database, which we're going to store information and get information back from it. And usually the way you do that is that we build a connection pool. You have multiple we have a pool of multiple connections that they are open when your application starts. And now every time you want to talk to the database, you get this connection from the pool, you do whatever you want to do, and you put the connection back in the pool. And that's exactly what we can see here. We can see the repository, we can see the pool behind the repository, and all the connections that we have to the database. Okay, really nice. And what we can do here is that, so one of the aspects of building systems, as we saw throughout the talk, is that we need to be able to understand what is going to happen with our software if something goes wrong, if a process misbehaves, or if something is not working as expected. And we can simulate those things here. So here I have a pool with a bunch of database connections. Imagine that for some reason, okay, the database decides to disconnect one of those particular connections. Okay, so you can see here that we have all those numbers. Those numbers are identifiers for each of those processes. Okay, so I can do this. Well, let's imagine that the first connection here, for some reason, the database terminates it. I can simulate this here. I can come here and say, I want to kill this process. And we are going to kill this process. And what do you expect to happen in this case, right? From what we said, there's going to be a supervisor that is going to notice that that process no longer exists. But it also knows that we asked it somewhere to have a pool with 10 connections. But if that process no longer exists, our pool has only 9. And the supervisor is going to notice that and is going to start a new process in its place. So you can see here that the one with 253, it's no longer here. But we have a new one at the bottom with a new identifier. With the new identifier, that's the supervision working. We can even be more drastic. Imagine that your pool implementation has a bug. You can come here and say, hey, I want to kill the whole pool and see if my software is going to be able to handle that. And when we do that, you can see that it cascaded because the pool was broken. It didn't leave hanging connections in the system. It brought all the connections down so it could start a new pool and handle everything properly. All right, so this is one example of how we can practically use those abstractions to understand about our software or to connect to a live system in production and understand what it's doing. Here, the same way with the process list, I can come to any of those processes, double-click them, and get more information. And this is one of the many tools we have available in the ecosystem for exploring how your code runs in production and exploring your abstractions. All right, so let's move to the final part of the talk. So let's sum it up. So I was talking about documentation first class tools. So here's the Elixir documentation, and you can generate the same kind of exploration for documentation for any project that you have. We have a central repository, which is called Hacks, I've talked about, where you do not only host your packages, but also the documentation. So we try to not specialize anything for everything. The same tools that we have for writing the language, they are there for the community to create packages and extend the language, right? And that goes from language abstractions up to tools like documentation. They're all hosted in the same place and explored in the same way. Okay, so here's an example of accessing the documentation from the terminal. Alchemist is a language extension that you add to Emacs. So this is an example of having improved language support through editors. And I'm not saying that everyone here should use Emacs. The reason I mentioned Alchemist is because it was the first project really to bring first-class support to Elixir to an editor. And today, if you're using Sublime Text, Atom, VI, we have good tools for all those different editors as well. And Alchemist was the pioneer for that. Here's HacksPM, how it looks like. You can access the website, get more information. It first started as a package manager for Elixir, but it grew to be the package manager for the whole Erlang ecosystem, and that's really nice. And that's it. If you want to get started, there are a bunch of ways to get started. So the most straightforward one is through our website. So you can go to elixir-lang.org. We have a guide section that has a couple different guides. So the first guide is about getting acquainted with the language, the data types, processes, and some syntax constructs. But we have advanced guides as well that covers this whole part of building applications with supervision trees as well, and guides that talk about metaprogramming and so on. We also have a bunch of books. So here on the website, we have the guide section, and on the right side, we have the learning section that has a bunch of different resources. Those are some of the books available out there, but we also have screencasts, podcasts generated by the community, and a lot of different ways for you to learn more about the language. Code School, for example, if you like the way the Code School of teaching that is interactive with videos, they just launched the course on Elixir, so there are many ways to explore that. So here are some of the books. And finally, I want to thank my company, Plataformatec. Elixir was built and designed there. We are really proud of it and of the community. And that's it. Thank you for your attention, and I'll take questions for 10 minutes, I believe. Thank you.
Thank you for the amazing lecture, and we have time for some questions. So, do you have any?
All right.
So firstly, thank you for a very interesting lecture, and my question is, how did you achieve that the modules from Elixir are portable and can be executed within Erlang itself without Elixir?
Okay, so the way I'm going to go a little bit, talk about compilers. So the way compilers work is that they have multiple passes, and they have multiple representations for all those passes. And Elixir decision, early one, was to target a higher level pass exactly to stay close to Erlang. So the short answer is it was an explicit design decision to make those things compatible. In order to do so, we are using most of the same compilation stack as Erlang. So after we parse the language and we build the AST, we make that look like Erlang and feed into the Erlang compiler. So that's a kind of an overview. And it's really interesting because, one interesting aspect of that is that it could constrain the language and the design decisions we can take, because now, we like it or not, we are bound to many of the design decisions that Erlang did. And that helps in language design because design language is a very open space and there are a lot of decisions you can take. And having that limit helps us stay grounded, right? Because otherwise it's very easy to just add too many features and lose control of the consistency that the language has. That's one nice thing. And the other nice thing is that by sharing a lot of the compilation stack, when we notice things that are slow, we can contribute that to the Erlang compiler and everyone wins. The compiler becomes faster for everyone. All right, thank you for your question.
Are there any other questions? Well, okay.
So thanks for that interesting talk. As you pointed out, a lot of what you were talking about already exists in Erlang and has for years, and you're just building on top of that.
Yes.
One of the new ideas you have is extensibility using macros, which of course is not a new idea. That's been around for a long time.
Yes.
But not in Erlang. So when you decided to add that to Erlang, how did you go about doing it? Which existing macro systems did you study and base your ideas on?
That's an excellent question. So, I like to talk a lot. I'll try to make it short, but I think this story is interesting. So when I first tried to design the language, I built a prototype, and it was a horrible prototype. Because, so for example, I was coming from Ruby, and I knew, well, I want metaprogramming. I want polymorphism. So I knew the things I wanted, but my reference was Ruby, and I tried to bring the way you do metaprogramming from Ruby, the way you do polymorphism from Ruby. So for example, originally the metaprogramming was evaluation of strings, right? Which is not ideal. The first version had a prototype-based object-oriented system because I was like, well, how do I get polymorphism? Objects, I guess. And So I took the decision because I want this. And the solution I knew were those solutions, but it didn't map well to the runtime. So I said, okay, I need to step back and I need to see how other languages they are solving those problems and try to bring those solutions and see how they map to the ecosystem. So and then the work of John McCarthy was with macros and everything was really helpful. And at some point I considered writing exactly a Lisp to leverage the macro system and have the mapping from what I see in my code is exactly the syntax that I am seeing here right now. But at the time, we also had already 2 or 3 Lisps running the Erlang Virtual Machine. And then I thought, okay, so what if we could go in the direction of MLisp, which is to have a syntax that is small, that is convenient, and has a direct translation to SLisp. So, the meta programming systems that we talk about, that I thought about at the time was the or being based on the evaluation of strings, or being based a lot on being able to change the code at runtime, which doesn't work for the virtual machine. And then the approach with macros, in the case, the Lisp style macros, which is the one we settled on. And there are probably many other options out there that I'm not familiar.
So that's nice, Hunter. I want to just summarize it for everybody else, because often people are talking about little details and not getting to reusable ideas. So there are 2 important reusable ideas in what you just said. Don't use Ruby, and do use Lisp. Excellent ideas.